Yeah, I think it has started recording. So, so today, last time we were looking at prime ideals. So we have an integral extension, and we wanted to take a prime and see we introduced this notion of primes lying above. And we said that integral extensions have this lying over property. If you have a prime downstairs, there is a prime upstairs lying above. Lying above meaning the upstairs prime intersected with the ring downstairs is your prime ideal downstairs. And then we proved as a corollary the going up theorem. And we also stated the going down theorem, where there was one more condition required. And then we had this explicit description, some hint towards that. That's what we have done last time, and let's continue. So let me start sharing the screen, today's lecture. Yeah, can you see the screen now? So I should get today's lecture, 7. Yeah, one of you please confirm.
Yes.
Fine, yeah. So today is Feb 4th, no? The date is correct, yeah, fine. So, we will discuss Galois extensions. We will continue to discuss. So, topic is going to be more and more interesting as we proceed. Okay. So, last time, so this is what I was just saying verbally. We discussed prime ideals in integral extensions. We discussed the lying over property. So, what was this property? If you have B over A integral, and if you have a prime P downstairs, then there is a prime capital P upstairs with the property that capital P intersection A is equal to small p. And this we proved. What was the main point of the proof? Can you quickly tell me? There were two ideas involved in this proof. One was
lemma and localization.
yeah, one is the localization trick, and then the other one is at some point we had to use Nakayama. Okay, and yeah, then there was a little bit more work, but we did that, and as a corollary, we did the going up theorem, and more generally the going up theorem. We also had the going down theorem where we needed one more condition, no, not just B over A is integral, but also A is integrally closed. Integrally closed. Base string is integrally closed. And last time Manav gave a counter example where the base string was integrally closed, but the ring above was not a domain. And I said for us, everything is a domain. And even amongst domains, you can give a counter example if you don't assume integrally closed. So think about that, or search and references.
So I found something online. If you
Okay, good, Manav. So maybe we can discuss, or is it easy, or it involves some things?
I put it on the chat.
No, chat I will not see. It's okay. We can discuss it later. I also found something which was not so easy, but it was doable. In fact, it was done here, so I did read that. But the point is, I mean, these are things that you should do. So if you have understood that, then that's fine. Okay, so others should also do the same thing. What I meant is later, meaning at the end, if we have time, anyway, we need to talk a little bit. At that time, we will take it up. Okay, so as long as you have these examples, I'm happy. So we also talked about the explicit description, which we recall just before starting today. Maximal ideals lying above a maximal ideal when the ring above is generated by one element over the base ring. Today we will continue assuming that the field extension is Galois. So let's start. A is integrally closed. A is integrally closed in its quotient field, which we don't usually say. Integrally closed meaning integrally closed in its quotient field, and quotient field is called K, and L is a finite Galois extension of K. Okay, this is the setup that you have. Therefore, you have a Galois group, Galois L over K. This is a finite group of order equal to the degree of L over K. Call it G, and let B be the integral closure of A in L. Standard setup. and then so you take a maximal ideal of A, uh, maximal ideal of A, and we would like to know what are the prime ideals lying in. So if bottom, if you have maximal ideal, then the prime lying above is also automatically maximal. This we have done. So we would like to know what are the prime ideals lying above, and you take two of those. So this is capital P and this is capital Q. Uh, so capital P and capital Q are two prime ideals of B lying over P. Then you know how is Galois theory coming in? We would like to make the claim that there exists a Galois element sigma. Would you like to complete the sentence? So if you have two
Okay.
prime ideals lying above this, there is a Galois element so that
Sigma of P equal to Q.
yeah, one is a Galois conjugate of the other, sigma P equal to Q. This is what we are going to prove, and so let's start the proof. Assume this is not the case. So what we know is both these are maximal, right? Because we have shown that prime lying above is maximal if and only if prime lying below is maximal. So both these are maximal, and because both these are maximal, if Q is maximal, of course sigma Q is also maximal for all sigma. So if this is not true, that P is not sigma Q, then you can conclude that these are coprime. Agree? So then these ideals are coprime because these are maximal. If one of them is maximal, then itself these two are coprime and both are maximal. So these coprime or co-maximal, whatever is the word. What I mean is the sum is the full ring. Okay. And if this is the case, what is the result that you know? Whenever you have co-maximal ideals, this result that you often use. What is it called? We have discussed this some time back also.
Remainder theory.
Say that again, louder.
Chinese remainder theory.
CRT, Chinese remainder theorem. Okay, so by Chinese remainder theorem, so if I give you x1 and x2, x1 and x2 in your ring is B, right? These are ideals in B. If I give you x1 and x2, then I can find an x in B which is congruent to x1 mod P and congruent to x2 mod this. This I can do. So I'm going to apply Chinese remainder theorem for these two with x1 as 0 and x2 as 1. Okay, so there is an x in B says that it is congruent to 0 mod P and 1 mod sigma Q, and we can do this for each sigma in G. Because for each sigma we know that P and the corresponding sigma Q are co-maximal, so you can do this. I'll add a remark because this morning I made a mistake, so I thought I will type up the mistake. So I made a mistake thinking that we can get X is congruent to any B mod P and X is congruent to any B sigma mod sigma Q for all sigma in G where B and B sigma are in B. This is also Chinese remainder theorem, but for this to be true, what do you need? You need the collection of all these ideals, P and all the sigma Q, all these should be mutually coprime, which we don't have. We only know that P and sigma Q are no, even that we have, right? Sigma Qs are, so we are saying that P is not sigma Q. P is not sigma Q, so all the sigma Qs are maximal. Okay, so here Q is typo. I should put the correct thing. And P is not sigma Q, but the collection of sigma Qs, yeah, they are also co-maximal. So it was not really a mistake. The mistake was okay. So I will rewrite this. So I'm saying that this would need this collection to be co-maximal, which is also true provided you know
No.
I'm counting correctly. See, what might happen is sigma 1 q may be equal to sigma 2 q. If sigma 1 q is not sigma 2 q, then they are also comaximal. Uh, Yes. So what is not true is corresponding to each sigma, if you give a distinct B sigma, then I may not get this because sigma 1 q may be equal to sigma 2 q. Sigma 1 q may be equal to sigma 2 q, and if B sigma 1 is not B sigma 2, no, even then I can get. So there was no mistake. But the point is I did not need that much. I am applying only to these two. So I will delete this remark. This is unnecessary. Okay, forget this.
You
I
don't
thought
need
yeah.
that B sigma 1 is equal to B sigma 2, no? Then, like, you will have to choose B sigma 1 such that it is equal to B sigma 2.
Then of course there's no problem. But even otherwise it's okay. No, suppose B sigma 1 is not equal to B sigma 2. Okay, so
Then it
I
is a
can.
problem, no? Because
I don't think there is a problem because you just take B sigma 1 and apply Chinese remainder theorem. So you will get an X which will simultaneously solve for B and yes, you are right. If you get an X which simultaneously solve for B and B sigma 1, and later when you take B and B sigma 2, when you simultaneously solve, that may be some other X prime. Correct, you are right. Yeah. Uh, but again, I will still delete this remark because only distinct sigma q you will consider. No, if it is the same sigma q, you will take only the distinct one. So comaximality is true. So I will just delete this remark. Anyway, this is all unnecessary because I am applying only to these two. And it's the same one that I am taking for each sigma. So there's no problem. So by Chinese remainder theorem, you get this. We can do this for each sigma. So x is in P and x minus 1 is in sigma q for all sigma. Okay. Uh, so x is integral over A, that is given to you. And therefore, what can you say? What is a norm? Norm is product of all Galois conjugates. So it is product of sigma x over sigma. What do you know about the norm? Because x is integral over A, each coefficient of the minimal polynomial is integral. In particular, norm is integral. So norm is integral over A. And where does the norm lie? Norm from L to K, what is the codomain? Where does it lie? It lies in K star. It lies in K. So it is in K and it is in A. It is in A because no, it is not in A. It is in K because it's a norm, and this is integral over A, and therefore I can conclude this belongs to A. Why?
integrally closed.
Because it's integrally closed. It's of course in K. Therefore this belongs to A. The answer is because it's integrally closed. It's in K and it is in B. Therefore it's in A. Okay. But norm is of what form? Norm is x times all the other non-trivial conjugates, right? It is sigma x as sigma varies. Sigma is identity also here. So x times the non-trivial conjugate. So it is x times something else. And this belongs to A, but where is x from? X is from, you have chosen x as that x is from, x is in P. X is in P. So x times something is also in P because it's an ideal. So norm belongs to P. So this belongs to P because X belongs to P and P is an ideal. So this product belongs to P, and therefore you know that norm X belongs to A and also in P. Therefore it belongs to P intersection A. But what is P intersection A? It is small p. So norm belongs to small p. Okay, norm belongs to small p. And we also have chosen X as that X is conjugate to 1 modulo sigma q, and therefore x does not belong to sigma q. Why? Because if x belongs to sigma q, x minus 1 is also in sigma q, therefore 1 will belong to sigma q, but that's not true. It's not the full ring. It's a maximal ideal. So
So
x is
one
not,
more.
yeah?
We saw that X does not belong to sigma q for some fixed sigma, right?
No, for any sigma, that is the remark that I was making here, because it's the same one, no? All your b sigmas is same. So it is true
No,
for
but
all.
how do you know you'll find the same X every time?
That's what Chinese remainder theorem told you, no?
Yeah, Chinese remainder theorem tells us just this much, right? This we find an x for this sigma.
Correct. But Manav, didn't you make a remark that if B sigma 1 equal to B sigma 2, then there's no problem? So we are in that situation, no? My number is 1. So for each sigma, so this is true for all sigma.
Because you are taking all the sigma such that sigma q1s are distinct. Sigma q is distinct. You're
Yes.
taking all the sigma I such that sigma I q is distinct, and you're applying the Chinese remainder theorem on this set.
No, no,
Union
no.
P.
Okay, so maybe I am wrong, but let me just say what I have in mind once more, and then we'll come back. Okay. So this is okay with you, no?
Yes.
Now suppose you take another tau.
Yes.
And if you have P and tau Q, then I can find an X such that X is 0 mod P and 1 mod tau Q.
Yeah, let's call it x prime.
You're saying that X prime can be different.
Yeah, but now, I think I got it now. So what I'm proposing is that you take the set of all sigma, like you take all sigma I such that sigma iq is not equal to sigma jq.
Yeah,
Take the maximal
they are
subset.
mutually co-prime. They are mutually co-prime.
Yeah,
And,
take all the maximal, take union with P and
yeah,
apply the Chinese remainder theorem on this whole set.
correct. So I need to slightly rewrite this. I will do that before uploading in Moodle. So here itself you are taking all the sigma q's, all the distinct sigma q's. They are mutually co-prime and apply the Chinese remainder theorem to that. So you will. So this also I will reformulate. We are doing it together. So what I initially did was the correct thing, not what I changed back. Okay. So this will come back. Fine, no? So you take the distinct sigma q's and P and this collection with distinct sigma q's. They are mutually co-prime and apply it together. Okay. So you have got an X which is 0 mod P and 1 mod sigma q for all sigma such that they are distinct. That's what matters for us. I guess. Let's see. Okay. So there's a small change that I have to do, which I'll do. So coming back to here, this is okay. This is in P. This is okay. And this is also okay, no? So what we have done as for the distinct sigmas, yeah, that's also okay, right? Because yeah, this is fine because if sigma 1 is not sigma 2, but sigma 1 q is sigma 2 q, we are only talking about this set. So this is fine. Okay, so X is not in sigma q for any sigma, and therefore sigma of X is not in q for any sigma, right? Take sigma inverse. So sigma inverse of X is not in q for any sigma, which means sigma of X is not in q for any sigma. But that would mean the norm is not in Q. Why is that? Because norm is product over all the conjugates, and Q is a prime ideal. So if norm belongs here, then at least one sigma X should belong to Q. So none of this is there. Therefore, the norm is not there in Q, and this is a contradiction because norm is in P. Norm is in P and Q is another prime lying over P. So Q intersection A is P and norm is in Q intersection A. In particular, norm is in Q. So this is a contradiction because norm is in Q. Norm is in P, which is Q intersection A. So norm is in Q. Okay. So the contradiction is, yeah. So this proves that. So we assume that P is not sigma Q and we got a contradiction. So all the primes lying above a maximal ideal, yeah, we assume P is maximal, and all the primes lying above a maximal ideal are Galois conjugates.
We never used that P as maximal.
We used P as maximal because we wanted to say that these are coprime, P and sigma Q are coprime, and that is because these are maximal. right? So these are maximal because P is maximal.
I think it is true for in general over prime ideals also.
Is
Then
it
we
true?
choose the element in a different way. The X, we don't use Chinese remainder theorem.
Okay, so in this particular proof for Chinese remainder theorem, we did use maximality, right?
Yes.
Yeah. And what is the other remark that you're making?
So suppose if we have a normal extension.
Are you saying that the result is true without maximality?
If it is a normal extension.
It is Galois.
Right?
It is Galois.
Yeah.
So are you saying that the result is true without maximality? That of course is correct. That of course is correct. I'm only talking about this particular proof.
Yes.
Okay. That of course is correct, and that's exactly my note which I was going to read out. So yeah, good. So we need not have assumed P is maximal. This is what you're saying, no? So and here is the proof. We need not have assumed P is maximal. Prime would do because you can localize. So you can localize and argue with the local rings AP and BP, and by what we have done using maximality. Now P is maximal in AP. No, PAP is maximal. So by the argument that we have given, so S is A minus P, and you would have got S inverse Q is S inverse sigma P. You would have got P times S inverse P, which is S inverse sigma P, and from this you can conclude that Q is sigma P. So it is anyway true. And how can you conclude Q is sigma P from this? Because these are prime ideals, you're using that fact. These are, I'm not saying S inverse I equal to S inverse J implies I equal to J. Not in general. I'm saying this is prime ideal, not just primes. S doesn't meet the prime ideal. So prime ideals are not intersecting the multiplicative set. Then it's easy to check that this implies this. It's injective. Okay, so this is what you had in mind, Manav, right? You just wanted to say that the result is true for any prime ideal, not just for maximal, and that's correct. And here is a proof. Okay, so this is the first thing. And now suppose A is integrally closed with the same notations. I'm just repeating quotient field, and E is a finite separable extension. I am not assuming normality, and the title is finiteness. So my claim is that if you have a prime below, if you have a finite separable extension and if you take the integral closure in that, there are only finitely many primes lying above that. Let B be the integral closure of A in E. Let L be the, yeah. So the claim is that there are at most finitely many primes lying above a given prime if you are if you are in an integral closure of a finite separable extension. So extension is finite and therefore you will get maximum, and the proof is obvious. We have already done it. So the earlier what we have done is for a Galois extension. So what you do is take the Galois closure of E. So let L be the smallest Galois extension of K containing E, and that is also finite. L over K is finite. And we can apply the previous result to this one. So we know that there are only finitely many primes lying above P in the integral closure of A in L. Why? Because all the primes lying above are Galois conjugates, and the Galois group is finite. There are only finitely many, and that's enough. So if Q1 and Q2 are distinct primes in B, B is the integral closure of A in E, and L is the Galois closure. Okay, so if Q1 and Q2 are distinct primes in B lying over P, consider P1 lying over Q1 and P2 lying over Q2. Okay, and so PIs are primes in the integral closure of A in L. So you can go further up, and in L, in the integral closure of A in L, you get P1 and P2. And so P1 and P2 lie over small p, no? Because Q1 and Q2 are over P. So P1 is over Q1, P2 is over Q2. In particular, P1 and P2 are over P. And uh, therefore,
Equal to sigma P1.
yeah, therefore, such collection is finite. The collection of Pi is finite because they are, yeah, because as you said, P1 is sigma times P2. But I'm also saying that P1 is not equal to P2. And why is that? Because Q1 is not equal to Q2. If, yeah, if P1 equal to P2, then P1 intersection that ring will be P2 intersection that ring, but that is Q1. So if P1 is P2, you will get Q1 is Q2. Therefore, P1 not equal to P2. And but there are only finitely many such PIs because it's a Galois extension, and we have proved that they will all be Galois conjugates. Okay, and therefore you have proved that there are only finitely many QIs, right? Because if there are Q1, Q2, Q3, there are three distinct things. And if you take P1, P2, P3 above that, so the collection of all the PIs is finite. Therefore, the collection of all QIs will have to be finite. Point is, if you take Q1 and Q2 distinct, then the primes lying above P1 and P2, they are distinct. But the total collection at the level of L is finite. Therefore, the collection at the level of E has to be finite. So therefore, there are only finitely many such QIs. Okay. Okay, so that's a finiteness condition. Now let me introduce two famous groups, okay, associated to what we have. Okay, three famous groups. One already you know because L over K is Galois, and there is a Galois group L over K. Now depending on a prime P and you have a capital P lying over P, there are two more famous groups associated with that capital P. One is called the decomposition group of the prime P, and the other is called the inertia group. Let's introduce both. So AKLB as usual means what? A is a domain, a ring integrally closed in K. K is a quotient field. L is a finite Galois extension of K, and B is the integral closure of A in L. Okay, and I'm assuming L over K is Galois, and G is the Galois group L over K. And if you take any sigma, then of course sigma B is B, because B is the integral closure, and you know that X is integral if and only if sigma X is integral. So sigma B is B, and let P be a maximal ideal. See, the general remark is, we can argue with maximal ideals and then do localization, and our results will be true over prime ideals also. So let P be a maximal ideal and let capital P be a prime lying above small p. So P is also, capital P is also maximal. And this is the remark, I have typed it up here. The results are also true for prime ideals by first localizing and applying our proofs, but we don't even bother. We are interested only in maximal ideals because soon we will be considering rings of dimension 1. You know this word Krull dimension?
Yes, like it.
Yeah.
My length of the length of a chain of prime ideals.
Yeah, so supremum of heights of chains of prime ideal, height meaning length, supremum of lengths of prime ideals. So that's a dimension. So in particular, dimension 1 would mean what? Every prime ideal is maximal. So we will soon be considering rings of dimension 1 because in algebraic number theory, those are the rings that will come. So we will be interested in Z and the integral closure of Z in finite extensions of Q. And all these rings have the property that they have dimension 1. We will prove it. We will prove it. So only those rings will come. So all the prime ideals that we are considering will be automatically maximal. Okay. But otherwise also these things can be proved for prime ideals by localizing, but we will not bother. So we will take P to be maximal. Capital P is also maximal. So every prime ideal is maximal soon. So this is Wolfgang Krull, 1899 to 1971, and yeah, so most of the mathematicians coming in our lectures are Germans. So he was also a German mathematician, and in fact you have heard this name once before in my class. Do you remember that? Maybe I did not say the first name at that time, but I did mention Krull once. Does anyone remember? It was rather quick. I did not stress it, but I did mention. Okay, let me remind you. I mean, just for fun, let me remind you. When we were discussing projective limits, this was lecture 4. In order to show that O by P is finite, Now, if O by P is finite, we show that O is compact by writing O as a projective limit of finite groups. And then we said in that topology it's automatically compact. At that time, I did mention Krull. Yeah, does it ring any bell?
I don't remember when.
Okay, yeah. So it was rather quick, and in fact, I myself remembered only suddenly today. So just for fun, I just put that here. So I think I have never tried this before. If I click this, it should come. So let's do. Oh, it will not come. Okay, it is coming. Yeah. Group, and fundamental theorem is true not for any subgroup but for closed subgroups. So closed is in that topology. So some textbooks might call that topology the Krull topology, K-R-U-L-L, Krull topology. Well, why I'm saying this is that's another place where typically students see projective limit in a very natural context. So the infinite Galois group, so if you have an infinite extension which is Galois, you have the infinite Galois group, that is also naturally a projective limit. And therefore Galois group is compact. Even in the infinite case, it's compact. Okay, I don't know whether it was audible. Anyway, you can check. It's there in Lang's book, Infinite Galois group.
It was audible.
It was audible. Okay, good. Yeah. So this does work. Okay, good. So the topology on the Galois group is called Krull topology. So it's the same Krull. I checked in Wikipedia. Okay, so anyway, so decomposition group, let's introduce. So G beta is the notation. G subscript, not beta. I said I might call it beta because for me, it looks like beta. But since I type it, I know it is capital P. It is math frac capital P. So it is G subscript capital P. And this is, so we know, right? Galois group acts on prime ideals lying above P, small p. Small p is in A, and you consider the collection of prime ideals lying above P, and the Galois group acts on that. If you take a P, if you take if you fix one P, then anything else is a Galois conjugate, meaning sigma times P, sigma of P. So now what we are saying is there is this Galois action, and GP is nothing but the stabilizer. I don't know the word that you use. When group acts on a set X, if you have X in X, you might call it the isotropic group or the stabilizer. What is the word that you have used?
Stabilizer.
Fixed group, stabilizer, yeah, stabilizer, fixed group, isotropic group, whatever. So GP is a stabilizer of P. That's a definition. Okay, so decomposition group is a stabilizer of P. The collection of those sigmas which actually fix P. Sigma P is P. So we have G acting on prime ideals above P, and GP is a stabilizer of P. So GP is acting on, yeah. Okay, so now note that, so G is acting on the collection of prime ideals, and you have an action on B by P. GP is acting on B by P. What is the most natural action? So how will an element here look like? It will be B small b plus P. And you take sigma from GP, and what will be the action? Sigma at B plus P. How do you want to define?
Sigma B plus P.
Sigma B plus P. That's the most natural thing, and you need to check that this is well defined. And this is well defined because if B belongs to P, you want to say that sigma of B belongs to P. But that is true because sigma is from GP. So if B is in P, then sigma of B is in P. Therefore, this is well defined. So you have this natural action. So this is well defined. And you of course have A by P is contained in B by P. And notice that this subfield A by P, P is maximal, this is a field. This field is fixed by GP, right? Why is that? If you take A plus P and if you apply sigma, sigma of A plus P you will get. And why is sigma of A? Because sigma is from Galois group of L over K. A is in K. A is contained in K. So this fixes GP fixes A by P. So GP acts on B by capital P, and it fixes A by P. So you are getting an automorphism from GP to aught of automorphisms of B by P over A by P. These are fields. B by P is a field, A by P is a field. Okay, so I wrote automorphism instead of GAL for Galois because you don't know separability, normality, etc. in general. But what we will do is, and what is a map? Sigma going to sigma bar. So what is sigma bar? Sigma bar is this map. Sigma bar of B plus P is sigma B plus P. So I could have put sigma bar here. Okay, that's the map, natural map. And inertia group, let me introduce. So under the assumption that A is integrally closed and L over K is Galois, we will show, not today, maybe in the next lecture or maybe next to next. I don't remember when it is coming. Maybe in the very next lecture we can show this. So we will later show that B by P is Galois over A by P. So instead of automorphism group, I can write Galois group. Okay, it is Galois. So you have this homomorphism sigma going to sigma bar, and we are going to show that this map is surjective. Okay, so this map is surjective. So you have a surjective homomorphism, and whether it's surjective or not, anyway, you can take its kernel, and the kernel is what is called the inertia group of P. So I have introduced the decomposition group. So Galois group is acting on primes lying above a given prime, and the stabilizer of a capital P, one prime, is called the decomposition group at P. And from the decomposition group to Galois group of B by P over A by P, you have this homomorphism. Happens to be surjective also. That's a theorem. And the kernel of this map is what is called the inertia group of P. Okay. So these two are very, very important groups. And Lang's notation is TP. So GP for decomposition and TP for inertia. But this is not today's topic. This is another day. And let us come back to decomposition group. And correspond. So decomposition group by definition is a subgroup of the Galois group. Galois group is a Galois group of L over K. So corresponding to a subgroup, you will get a subfield, right? This is fundamental theorem of Galois theory. You will have the fixed field of GP, which is called LD, D for decomposition. Okay, so we get LD, which is a fixed field of GP. So Galois group of L over LD, L over LD is automatically Galois, and the Galois group of L over LD is GP. The full Galois group is G, and this highlighted Galois group is GP. So Galois group of L over LD is GP, and let BD be the integral closure of A in LD. Okay, L over K is what is given to you. You have the decomposition group, and you take the corresponding field, and you take the integral closure of A in that field. And so small p and capital P are given to you, and you take the intersection of capital P in that intermediate ring BD, call it Q. So Q lies above P, right? Q is a prime lying above P. And do you see this remark that capital P is the only prime of B lying over Q? How many of you see this remark? I mean, see the proof of this remark. So we have the decomposition field LD, and you have the integral closure there, and you are taking Q to be P intersection BD. So by definition, P is lying above Q by the definition of lying above. But the claim is this is the only prime lying above Q. Why is that? There is no other prime in B lying over this Q.
Because sigma of P was equal to P, right?
Correct. So anything else has to be a Galois conjugate. But what is a Galois group? Galois group is GP. And GP by definition is any sigma in GP, sigma P is P. So there is no other Galois conjugate possible. So this is the only prime. You are right. Yeah. So this is only prime. So why?
But for that we require that something is a Galois extension of BD, right?
Yes,
You're using that D as a Galois extension of BD.
No, this is Galois. No? This is Galois. Whenever you have If L over K is Galois, the top part is always Galois. It's the bottom part which may or may not be Galois. Right? This may or may not be Galois, and as you know, what characterizes whether this is Galois or not? What I am highlighting now, that may or may not be Galois. When will it be Galois? What is a fundamental theorem? Fundamental theorem tells you that this is always Galois. If you have a fixed field, then this anything, any extent, any sub-extension, this part is always Galois. This part need not be Galois, but it is Galois if and only if see what needs to be checked is not separability. Separability must have been given to you when you said the full thing is Galois anyway. So what has to be checked is normality. And that word tells you, what the answer is. Normal. So what is the answer?
The Galois group should be a normal subgroup of L
So
over
this Galois group should be a normal subgroup. Then you can take the quotient, and quotient is a group, and that will be the Galois group of this. You must have done this, no?
Yes.
Or
I've forgotten.
maybe you had a problem that semester, right? Maybe not everything was which was supposed to be done was done because of lockdown. Is that correct?
No, I did it in the year before that.
Okay. But it comes in that semester, right? It comes in the spring semester.
Yes.
Yeah, so I don't know how much was done, but anyway, so these things we will assume. So anyway, this is okay. So your question is answered anyway. This part is automatically Galois. So this is okay, only prime lying above. Now take the cosets. So GP is contained in G. Take the cosets. Let sigma j be the coset representatives. Coset decomposition of GP in G. And then note that same argument, sigma j p are precisely the distinct primes lying above p. Because sigma j's are distinct, these are coset representatives, and you know that sigma j p will be another prime lying above p, and there is nothing else. By the same argument, because uh, because if you take two primes lying above p, they will differ. So fix p, fix capital P, and anything else will be a Galois conjugate of capital P. And you can take all these Galois conjugates, they are all there, and any other Galois conjugate is coming from GP, and that fixes P. Okay, so if sigma j GP equal to sigma k GP, that is same as saying sigma j sigma k inverse belongs to GP, and therefore sigma j and sigma k will not be distinct. So if you take distinct representatives, they are exactly the distinct primes by the same argument because it is GP. Okay. Also check the following that this is easy. You consider sigma p and consider its decomposition group. So decomposition group is defined for every prime. So if you consider this prime sigma p, what will be its decomposition group? Take a guess, and most likely your guess may be right. Answer has to be in terms of GP. And can you take a guess what this is? Of course, you can work it out, and then of course you will get the answer. But without working it out, can you take a random guess? From one group, how do you get another group? Yeah.
Compose sigma with GP.
Compose?
Sigma and GP. Like every element in GP compose with sigma.
Will that be a group? That may not be a group, no? That may be a group only if it's abelian. Is that a group even in that case? Because you're saying take sigma tau. That's what you're saying, right? So sigma tau 1 and sigma tau 2, if you compose, no, that's not a group even in abelian case. Because sigma tau 1 times sigma tau 2, even if you can permute, you will get sigma square tau 1 tau 2. Maybe that's okay. But anyway, you can't even permute. It's not a big deal. But how do you get a group from given a group and given a subgroup H, given a group G and given a subgroup H? How do you get some more groups? There's an obvious way in order to get more subgroups, no? Take its conjugates, right? G and G inverse. So this will be sigma. So you were close to it. It is sigma GP sigma inverse, and you can easily check. Apply the definition. So anything in this will be of the form tau sigma p is sigma p. But if tau sigma p is sigma p, then sigma inverse tau sigma fixes p. So sigma inverse tau sigma will be in GP. So tau will be in sigma GP sigma inverse, and exactly same way other way. Okay, so there's a close relation between the two. And now we are going to make an observation, make a claim that this decomposition field LD. So this is the decomposition field. This has a property. So first of all, we have observed here that if you take P here and the corresponding decomposition field you write down, the prime ideal here, which is P intersection the ring here, which we call Q, and we have observed that P is the only prime of B lying over Q. This we have already done. This we have already seen. P is the only prime of B lying over Q. Okay, now you ask the question. Suppose K is there, L is there, and take a subfield E, and does it have this property? What is the property that I have in mind? P is the only prime lying over the corresponding prime in E. So what is the corresponding prime in E? You just take P intersection E. P intersection E will be automatically part of P intersection the corresponding ring. So P intersection E is an ideal, and suppose E has the property that P intersection E, P is the only prime lying above P intersection E. Is what I'm saying clear? You have K, you have L, and you are interested in intermediate extensions E, and you are interested in E with the property that P is the only prime lying above P intersection E. Are there such fields? Can they be such fields? Yes.
We just saw one, right? We just saw one, right? LD. Up there.
Yeah, LD. Yeah, it's not very clear in the voice. Yeah, but now I heard you. So LD is one such example. Okay, so that means that set is non-empty. There are such fields. But now we are going to characterize LD as the smallest such field. So LD is the smallest subfield E of L containing K with the property that P is the only prime of B lying over P intersection E. Okay, this is also obvious. So let's write down a proof. Among such fields, this is the smallest extension of K. Among all those fields containing K, this is the smallest such thing. Okay. So we have already seen that LD has this property. Now, if E is strictly contained in LD, suppose E is smaller than LD, we want to say LD is the smallest. If E is smaller than LD containing K, I forgot to write, containing K is understood. Okay. Then Galois group of L over E strictly contains the Galois group of L over LD, which is GP. Okay, this is from Galois theory. And because this strictly contains, there will be a sigma here, which is outside this. And because sigma is outside this, sigma P is not P. So there is a tau outside this, and tau P is not P. But both these lie above P intersection E, and these are two distinct primes lying above P intersection E. So only prime is not true. So that shows that. Okay. So it has the property that it's the smallest subfield of L containing K with the property that P is the only prime of B lying over P intersection E. Okay. Now we are going to show the following. LD has one more property, which is that LD has one more property, which is that you take the corresponding So what is the word for this? Yeah, I think in many places this is what is called the residue field. Okay, so P is a maximal ideal. You take A by P, that's a residue field of A or the residue field of K. And similarly, you take the residue field of BD. Okay, these two residue fields are equal. Okay, so we are going to show that at the base level and at the level of the decomposition field, these fields, the residue fields, are same. So let's prove that. Again, you know, this is an application of Chinese remainder theorem. So Q by definition, the notation Q stands for P intersection BD. So that's a notation, and we are going to use Chinese remainder theorem again. And so take sigma outside GP. Take sigma outside GP, and then you know that sigma P is not P. And also sigma inverse P is not P, because if sigma is outside GP, then sigma inverse is also outside GP. So you have these things. And let us denote sigma inverse P intersection BD by Q sigma. Okay, sigma inverse P intersection BD denoted as Q sigma. And the first claim is Q sigma is not Q. Q is this. Q is this, and Q sigma is this, and Q sigma is not Q. Can you try to give me an explanation for this? What happens if Q sigma is Q? So this, if this follows from anything on this slide, what is your natural guess? Where should this follow from? There's only one thing.
Sigma inverse P is not equal to
Right.
P.
It should follow from this. Now, does it follow from this automatically? Is it set theory or is it something else? It's not set theory, right?
No,
Because
we can have
the,
sigma of sigma inverse P is equal to P, right?
right.
Their intersection like makes sense of the other thing.
Yeah, so intersections agree does not mean the originals agree. So it's not set theory, but still you can conclude this. Why? Because you know this is LD, this is a decomposition field, and this has that property. What is the property? I'm not using smallest. It has that property that there is only one prime lying above. P is the only prime lying above O. P is the only prime lying above O. Similarly, sigma inverse P is the only prime lying above O sigma. So if O sigma equal to O, then P is a prime lying above O, and sigma inverse P is also a prime lying above O, and they are not equal. So you will have two distinct primes lying above O. If these are equal, then you will get two distinct primes lying above O, but that you cannot have. P is the only prime lying above O. So this is
over there, didn't we have sigma P equal to P or something? Like we had that P was such a ideal such that sigma P is equal to P. We had that over there, right?
correct.
For all sigma.
Yeah, correct. No. So no. What we have is sigma P equal to P for all. That is what was defined as GP. GP consisted of those sigma such that sigma P is P. Now I am taking a sigma outside GP. Therefore, sigma P is not P. Okay. The property that I am using is LD has the property that capital P is the only prime lying above B intersection LD. B intersection LD is what is called Q. P intersection LD is same as P intersection BD. That is what is called Q. Is it okay, Manav? It is written down here, so let's read it out. Indeed, if Q is Q sigma, then two distinct primes. What are the two distinct primes? Namely, sigma inverse P and P. These are distinct by the choice of sigma. And both these lie above Q. Sigma inverse P lie above Q because of this. If Q sigma is Q. And P lies above Q is given to you. So you will have two distinct primes lying above Q, which is not possible because LD has the property that P is the only prime lying above P intersection LD. Okay, therefore Q sigma is not Q. And Q sigma, all these are maximal because we are always assuming P is maximal. And therefore you can apply Chinese remainder theorem. And exactly the same confusion I had earlier might come in the next slide. So we have to fix this also. So I may have to, so let me just see there. I may have to apply this for all sigma. For all sigma. So that means come back here. I have to fix this here. I have to get some mutually coprime. So all the O sigmas are maximal, but I would like to get mutually coprime. So I would like to get Q, not O, Q. So Q sigma and Q tau. Suppose you take sigma and tau here outside this. I would like to get Q sigma and Q tau also to be coprime, but I will get that if they are distinct, right? Because of maximality. So I will get Q sigma and Q tau. Either they are equal. If they are not equal, they are co-maximal. So I can apply Chinese remainder theorem to the collection of Q sigmas and Q, where the Q sigmas are distinct, exactly like earlier. That's what we will do. I will need to correct my slides. So all these are maximal. So CRT applies. So let X be any element in BD. Remember what we want to show. We want to show this. And this is a containment, right? A by P is anyway contained in BD by Q. So what do you need to show in order to show that they are equal? There is it's a containment. There is an obvious injective map from the left to the right. So in order to show that they are equal, what do you have to show? You have to show that it's a bijection. So you have to show that it's a surjection. It is onto. So given an element here, you have to get a pre-image. So you have to start with X plus Q, where X is in BD. That's what we are doing. So let X be an element in BD. Let X be in BD. And we will do, using Chinese remainder theorem, something so that we will get something in A by P. Okay, so if X is in BD, there exists Y in BD such that Y is congruent to X mod Q and congruent to 1 mod Q sigma, because of the co-maximality. But I would like to do this for all sigma. I would like to do this for all sigma outside G beta, outside GP. So what do I need? I need, yeah, this is fine exactly as earlier. So all the distinct Q sigmas are mutually coprime. So I can take the collection Q and all the distinct Q sigmas, and I can apply Chinese remainder theorem together. Okay, where I am taking one for each of the Q sigma, and I get such a Y. Okay, in particular, so this means Y minus X belongs to Q, but Q is contained in P. And similarly, Q sigma is contained in sigma inverse P. That was the definition. Q sigma was sigma inverse P intersection LD. So Y minus 1 is contained in this. In particular, Y minus 1 is contained in this, and this is true for all sigma. And the second congruence we can write down as apply sigma. So Y minus 1 belongs to this. So sigma Y minus sigma 1, which is sigma Y minus 1 belongs to P. So you can write this like this. Now what are we going to do? We are going to take this congruence, this congruence, and all these congruences together, and I'll take the norm. Okay, multiply all these together. Multiply all these together. This is true for G minus GP. Okay, let's. So this is true for all sigma outside GP, and now we are going to consider the norm map from LD to K. Okay, so LD to K, what will be the norm map? So this may not be Galois. LD to K may not be Galois, but whatever it is, these are products of the Galois conjugates. So from LD, you take the K morphisms of LD. It may not land in LD. That is normality. That may not happen, but still, you have the Galois conjugates, Galois elements, sigma from LD to the algebraic closure of K. So it will land in L, because L is the Galois closure of, because L over K is Galois and this is a sub extension. It will land in L. You take those things and take the product. So consider the norm map from LD to K what will be the sigmas which will contribute to this norm map? These are sigma from LD to L. So exactly things outside GP only will contribute, because things from GP has a property that they fix LD. They are identity on LD. So what contributes to this norm map? Of course, identity map, and anything else, non-identity meaning things are outside GP. So what will contribute is precisely what you have calculated, because these sigmas are outside GP, and so norm map will involve product of taking product of this and all these. So sorry. So the norm of y, right? You take this one and you take all these. So the norm of y will be the product on the left hand side, and the product on the right hand side is x times 1 times 1 times etc. So that is x. So that is x mod p. Okay, this is what you get. But the norm also lies in k, because norm is from LD to k. So norm lies in k. And y is from where? Y is in BD. So that means BD is the integral closure. So y is integral. Y is integral over A. And because y is integral over A, norm is also integral over A. And therefore, what can you conclude? Norm belongs to A, because A is integrally closed. So it belongs to A because A is integrally closed. Same argument that we applied earlier. Okay. And now this, so what did we conclude up to now? We have this thing, norm x, norm y minus x belongs to P, but norm y belongs to A, and in particular in B. I'm going to use only B here, not B, BD. So norm y belongs to A, in particular it's in BD, and x is from where? X is also from BD. We started with an x in BD. X is in BD. So both left hand side and right hand side are in BD, so the difference is in BD. So if you know that the difference is in BP, difference is also in BD, so difference is in P intersection BD, which is O. Right? O is the intersection of P and BD. O is the intersection. So difference is in P. That's what we have concluded. Difference is also in BD. Therefore, difference is in O. Not O. It is Q. Difference is in Q. So we have concluded that this is congruent to X mod Q. So the changes I have made P to Q because of all these arguments. Okay. But now you are done. What do you have to show? And both sides are in BD, and we wanted to show that this natural injection is surjective, right? That's what we had to show. Our claim is that these two sets are equal. So that means this is a surjection. This is anyway an injection. So this natural injection is surjective. So that's we have done, right? We have arbitrarily taken an x from BD, and we are showing that x mod Q is norm of y for some element y, but norm of y belongs to A. We have shown that norm of y belongs to A. So given any x here, corresponding to that, you have got this pre-image norm of y. So norm of y goes to x. So this is surjection. We have just shown that any x in BD has a pre-image, which is norm of y that we constructed. Therefore, these two sets are equal. That's what we wanted to show. Okay, so I think it's a good time to stop. So what we have done today is, if over Galois extension, if you have a prime below and a prime above any other prime, so all the primes lying above are conjugates of each other, Galois conjugates of each other. As a corollary for any separable extension, we showed that given a prime below, there are only finitely many, at most finitely many primes are there above. There are only finitely many primes lying above. And this we proved by going to the Galois closure. And then we define the decomposition group as a stabilizer of, so Galois group acts on the set of primes lying above, and decomposition group is of P is a stabilizer at P. And then I stated a result which we will prove later, that there's a natural action on d by p over a by p. So you get a map from decomposition group to the Galois group of this residue field extension. And I said that we will prove later that it's surjective. Its kernel is called the inertia group. And then we define the decomposition field. Observe that it has this particular property, that it is the smallest field, such that smallest field contained in L and containing K, such that P is the only prime lying above P intersection E. That property is there. And finally we prove this result, that A by P is BD by Q, where BD is the integral closure of A in the decomposition field LD. Okay, I think it's a good place to stop. We can talk for some time and then we'll stop. Yeah. So I will stop sharing the screen. Yeah. So we can talk. We have some time. We have 10 minutes. So if you have questions, etc., we can talk a little bit, and then you can leave. So maybe I can stop recording.